In the last 50 years, industrial gases, and especially air gases, such as oxygen, nitrogen, argon, and hydrogen, played a major role in the development of the new metallurgical processes. Air Liquide pioneered the importance of developing technologies for the use of industrial gases in steelmaking. In the 1950s, the development of the OBM process was made possible by a tubing system to enable oxygen injection at the bottom of the steelmaking converter. This breakthrough technology was invented by two Canadian engineers working at Air Liquide, Guy Savard and Robert Lee. The first trials of inert gas injection, such as nitrogen and argon, through molten metal, gave birth to the Gazal process. This technology is still used today in many foundries for the desulfurization of cast iron or the refining of aluminium. In the 1970s and 80s, the explosion of energy prices encouraged the development of oxygen-based combustion technologies to reduce the consumption of energy, while improving productivity and reducing the volume of fumes to be treated. Air Liquide worked in collaboration with the industry, steelmakers, foundries, producers of aluminium and recycled metals, to develop special oxygen burners and combustion processes. An integral part of our strategy as a major industrial gas supplier is the collaboration with our customers for the development of technologies for their industrial processes. To do this effectively, we must understand the complexities of their operations. Common goals we have with our customers include continuously improving their production efficiency to overcome serious threats created by world competition, adapting processes to the fluctuating prices of energy and raw materials, being cognizant and respectful of the new regulations as they emerge, finally and above all, aiming at more sales growth of new products. Each one of these elements is stimulating the growth of our portfolio of industrial gases technologies. Here are some examples illustrating this activity in research and development. Development of supersonic lances for safely and efficiently injecting large quantities of oxygen into the electric steel furnaces and converters. Development of low NOx oxygen burners for reheating steel before it is sent to be rolled. Development of in-situ optical devices for the quality control of atmosphere in the aluminium and steel smelting furnaces. And finally, the development of helium-based gas mixtures used for the fast cooling of motor transmissions for the car industry. And now I would like to invite you to discover all our activities here at the Research Center and at our customer sites. The tunable diode laser is an instrument which allows us to measure gas composition. To do that, it uses the gas property, which consists in absorbing a certain number of wavelengths. The advantage of this apparatus is to carry out in-situ measurements in real time and almost without maintenance. The optical signal is sent by an optical fiber and is then recovered by a receiver, which transmits the electric signal by a coaxial cable. Several gas species are measurable by the laser diode, in particular the gases which absorb in the near infrared. CO, CO2, and water vapor at low temperature are some examples. Several research studies are being conducted at Air Liquide on process optimization and atmosphere control developments. In terms of process control, we're developing a diode laser-based measurement system for the electric arc furnace, where we measure CO and CO2 to optimize the oxygen injections in a post-combustion process to maximize total power input to the steelmaking process. After steel, aluminium is the second most used metal. Today, a third of this aluminium produced comes from the recycling of products. One of the most used methods is the rotary furnace. These types of furnaces are often equipped with oxy-combustion burners in order to maximize productivity and energy savings. Air Liquide collaborated with several of its customers on the new solution for this type of process, called Recherche. Recherche is a continuous optimization process of the furnace based on gas analysis by diode laser. This new technology allows to make measurements at very high temperatures, in situ and in real time, in environments highly polluted with dust. The information sent by the sensors is then transmitted to a process logical controller, which calculates in real time the optimal furnace operating conditions. Thanks to this control system, the oxidation of aluminium is strongly reduced, its productivity is improved, and the oxygen and natural gas consumption are reduced as well. The industrial validation process showed savings up to 20 euros per ton of aluminium made. A significant part of our research activities requires the essential use of modeling. Our researchers in fluid mechanics develop models which allow us to consider various parameters, such as temperature, pressure, concentration, different geometries, to evaluate their impact. We save precious time and money by avoiding difficult and often expensive experimental campaigns. Once the operational parameters of the prototype or the process are being defined by the modeling stage, the second step concerns validation on a pilot scale, which can be carried out either in the research center or at the customer site. This stage is critical to the model's validation and to the readjustment of all the preset parameters. We're here in an electric steelworks, where steel is produced from this recycled scrap. The first stage in steel production is the arc furnace, where this scrap is melted. Our concern at Air Liquide is not only to optimize oxygen injection in the furnace, but also to optimize the injections of coal and natural gas by proposing innovative solutions. These consist of regulating injection of coal, oxygen, and natural gas by a continuous fume control system that uses information from a diode laser. We're able to improve its output by ensuring a better heat distribution within the furnace. An improved combustion process offers a better fume emission control system. Direct flame reheating furnaces equipped with gas or fuel burners and preheated air are used to heat steel up to the rolling state temperature. The steel pieces are slowly heated up while they continuously move through the reheat furnace. These furnaces, often of old designs, are a bottleneck for the whole production line. Air Liquide recently developed an innovative oxy-combustion solution called Alrol. This technology allows us to increase the output of the furnaces, depending on their requirements. The Alrol solution consists of adding oxygen burners to the existing furnaces to increase the furnace performance. Most of the work is performed during normal furnace operations, with a minimal shutdown for final installation. The flames generated by the burners significantly increase the thermal transfer to the load. Therefore, the reheating rate is largely accelerated. We're here on the site of a transmission manufacturer for large trucks, which uses metal heat treatment for the production of its parts. Air Liquide offers customers its expertise in the field of heat treatments. The heat treatment step is essential in guaranteeing a satisfactorily long shelf life for these transmissions. These treatments depend on the gas exchange process between the produced parts and the gases supplied by Air Liquide. The traditional heat treatment processes require important technological developments to comply with the new environmental regulations. Thanks to its research and development, Air Liquide is actively pursuing the development of new technologies, such as steel hardening by quick cooling of steel parts with gas, which allows us to effectively replace traditional processes of steel hardening in oil baths. As you've noticed, our activities in research and development are dictated by the evolution of our markets and thus our customers' expectations. It is then critical to work in partnership with our customers, creating common interest R&D teams while working on the same projects, to define technological action plans and their timely completion. By way of these partnerships, we offer our expertise in gas technologies, from gas production, online analysis, to continuous processes of our customers. The Primary Metals and Material Processing Group of the Claude Delorme Research Center conducts developments aimed at optimizing the environment and the performance of industrial processes involving gas-metal interfaces. In our view, the future requires a strong Air Liquide participation in the European iron and steel industry research effort engaged in the development of low CO2 emission processes for primary steel making. Within this framework, our residual gas separations units will allow the sequestration of carbon dioxide or its recycling for other applications. Our developments also concern emerging technologies, such as plasmas for thin-layer deposits on metal surfaces, to add new functionalities. These two examples show the large diversity of our project's portfolio. It is supported by an extensive expertise, by the international recognition of Air Liquide and its academic and industrial partners. This enables us to offer our customers cutting-edge technologies.